Absolutely.
Uh, hopefully what we're going to see when we go through some of those is that there's some patterns to them. Some of them I didn't necessarily expect you to get, so don't feel like panicked if you didn't get them all. I did record that extra video with a few explanations on that, but then we can talk about some other ones as well as needed. So before I get to the last page, anything on page 1?
Should we do H?
Yes. I believe that did I figure out a way to do H? Someone asked me about that earlier. Nick, did you ask me that? I think I said the only way to do H was to look at your calculator. Multiplying it out doesn't do anything. And trying to factor it out didn't really do anything. So looking at a graph, I think for that question in particular was really the only way to do that.
We kind of talked about how like the fact that we factored it out, we can't cancel anything out, so it just kind of shows us it must be.
Yes. Yeah, and that's kind of what we came down to on that question. Like you can FOIL it out, but things don't cancel enough. I tried to factor it using a difference of cubes. It's not supposed to be like tricky in that way, but what people have problems with limit stuff is that you want to like have things kind of be in categories, that something always works or something always doesn't work. And it just kind of isn't that way. Like limits, the way you have to work through them is kind of a mental checklist. Try to plug it in first. If that doesn't work, try to factor. If that doesn't work, conjugate. If that doesn't work, you can do simplifying complex fractions. If that doesn't work, go check your graph. So that's kind of always the backup for that. And that's usually why there's one in there that you can't do without your calculator. I don't know if that helps at all, but yeah.
Just type that straight into the calculator.
Mm-hmm. Yeah, not the limit part, but just type the equation into your graph and see what's happening around 0. Do you want me to show what is happening there? I can try to pull that up. Let me see if my calculator comes up. While I'm waiting for that, anything else on the first 2 pages that we were unsure about?
Back to on H that we were just looking at.
Yeah.
My Wi-Fi kind of kicked me out when you were talking about it.
Yeah.
So when I graphed it,
Mm-hmm.
it still looks like it doesn't exist. Is that accurate?
Typically, yes. If you go through kind of your mental checklist and none of our algebraic methods work, usually what's happening is that it's an asymptote there, which means it just doesn't exist and you can't do anything about that. So
okay,
we just don't like to say does not exist because one of our methods doesn't work. You always want to check your graph to make sure that there's a legitimate reason that it doesn't exist. You don't want to just like, well, I couldn't do it with algebra, so I guess it doesn't exist. And that's kind of not the way we want to think about it, but that is typically what will happen. Yes.
Okay.
Let me just type this in real quick. 3 plus x, whoa. Computer's freaking out on me. Minus 8 over x. Oh, come on. Let me see. I've got this right. Of all buttons to get stuck on my computer, the X button. Like, seriously?
Oh.
I know. I got to use it all the time. It's not helpful to me whatsoever. Okay, there's what the graph looks like. It's kind of a cubic looking thing. So if we're looking for the limit as x approaches 0, I maybe wouldn't like bank on just that being the only part of the graph you look at. I would probably zoom out on this and just make sure that something isn't happening funky. There's not another branch to this. No, in fact, there is. So that's a good one to look at. So there are actually 2 branches. So if I'm approaching 0 from the left, we saw this branch goes down to negative infinity. If we approach 0 from the right, there's another branch here going up to positive infinity, which is why it does not exist for us. But checking a graph to make sure that the ends go in opposite directions is always a good plan for that kind of question. Let's see, switching back, homework. Anything else then on page 1 or 2 before we hit page 3?
Could you do D on 2?
Yes. I believe that D is similar to one of the questions on the other, very similar to 4A. That's another one where there's nothing you can do. I can't replace the x's because of the, or I can't replace the signs because the x plus sign, you really can't do anything about that. So if there's no way to manipulate this, then the answer is check your calculator graph and see what's going on with that. So in B, I would go ahead and graph this, making sure that I type it in correctly.
Couldn't you technically do, since both are being divided by x, it also equals x divided by x plus sine divided by x,
Yes.
and those both equal 1.
Yeah, that's what's different than 4a. Let me see.
Oh, 4a? Are we talking about D?
Oh, yeah, we are still. But that just came back to me in my head there. There was a reason that 4a doesn't work, and there's a reason that this one does. So, yes, you can do that one. Thank you for reminding me of that. I've been looking at so many different ones of these. So let me get off my graph here. There we go. That I forget which ones are which. Yes, because the plus sign is on the top there, you can actually separate this into two parts. So the first part would be x over x. The second part would be sine x over x. So that's technically, even though you don't have to write it this way, finding two separate limits. X over x would reduce to 1. And then we know from our special trig limits that the limit of sine x over x is also equal to 1, which is why you end up getting a limit of 2 for that one.
So
Gotcha.
even though that the zero's on the bottom for the x over x, you can still say it's 1.
Yep, it's because you're going to actually, I'm not actually plugging in 0. I'm still simplifying that to 1. And then there's nowhere to plug the 0 in. So you're simplifying before you're plugging in.
Okay.
Still 1. Anything else on that page? All right, now let's have fun. Trig limits. I'm gonna just, I have a pen here. Start giving me question numbers. That way I can kind of like categorize them and maybe not have to do every single one of them if they're similar to each other. So, which ones do we need to go over?
1D.
1D,
1E, please.
1E,
1F,
1F,
1H.
1H.
1I.
Oh boy, we're gonna have fun here.
1K.
1J.
K.
Okay. Did I hear J?
K.
K.
2
What?
in general.
2 what?
Just 2.
All of 2. Okay.
Go over any of them in 3. It doesn't matter which one, just any of them in 3.
Oh, for 3?
Yes, 3K.
B, B, I, and L.
3.
I mean, yeah. B, I, and L.
Okay. I'm just gonna start with what we have, and then if we like run into some things that seem the same, we'll go back and try to fix that. Let's see. What's an easy place to start? D is not an easy place to start. Neither is E. F and E will be similar to each other. Let me start with H on 1, and then I. K and D will come as a result of I. Okay, so that's kind of going to be my plan here. H is probably the most straightforward one out of the group we've talked about or looked at in question 1. And it's because it's very similar to one of the notes ones that we did. This looks very close to one of our special trig limits, except for that 7 right there. So really what you're thinking about this as is like a 1/7 times sine x over x. What did we say the limit of sine x over x is?
1.
1.
So 1/7 times 1 just gives me 1/7 for that. So for those, there's not a whole lot of manipulation. You're just looking at the number kind of in the front of it, and that's really going to be your limit. Now, I looked at I. Did we see the extra video that I made on Friday or no?
No, I didn't see.
Okay.
Yeah, I saw it.
Announcements. I had quite a few questions, so I was trying to kind of put off some of this, not put off, but like help so that you're not so stuck on your homework. So I actually did I and a couple other questions on that video, but so this is what I did there, but I'll show you this. So for something like it's going to look really funny what I'm doing to begin with, but what I said in the video on this is that I am not looking for you to do this every time. There are some of these that we do this to see why there's a shortcut to it, but we're not going to do it every time. You're just going to kind of learn the rules. So you're going to see what I'm talking about here in a minute. We don't have a rule for a sign over a sign. So what I'm going to do to this, and just kind of stick with me for a minute. Again, I'm not looking for you to do this every time. Also understand that there's not going to be this many trig limits on the test, and there's none on the quiz. So that maybe will help our panic level. I am going to multiply by something next to this to simplify it, and you may only multiply by a form of 1. So just stick with me for a minute. I'm going to multiply 5x and 6, top and bottom. Now, how are you supposed to know what to do with that? Again, I'm kind of showing you what's happening here so that you don't have to do this every time. So I'm going to kind of manipulate this around. I am going to take this sine of 5x, and I'm going to put it over this 5x because everything's multiplied together. So I'm just going to kind of work through this, and I'm going to put that over this. I am then going to take this sine of 6x and put it under that 6x. And get that. And then the leftover 5 on top and 6 on bottom, I'm going to stick out front. Okay. So what did we say? Because we did talk about this in the notes. What happens to that when it's a 5x and a 5x? That simplifies still to what?
1.
1.
And I know this is upside down, but the reciprocal of it is 1. What's the reciprocal of 1?
1.
1. All right. So that simplifies those. What's left?
5, 6.
5, 6.
Just 5 over 6.
Mm-hmm. So do you see how the answer to this with a little manipulation works out to 5, 6? Well, what's my main point of that? Go back and look at the original problem. Without doing any of the work, how are we going to, from this point, get our answer?
Just look at the
Yeah.
5 or 6.
And not because that's necessarily a rule you have to memorize. I just showed you why it works, but I don't want you to have to do that every time. So there is the simplified version. It is kind of something that shows up a lot. You'll see that is very similar to D. There are other ones in here too that are like that. A on question 3. I don't know. I feel like it comes up again, but so that's kind of our rule of thumb for that. Well, now look at I and use I on question D up here. So using that same thought, if it's a sine over a sine, we said it was just going to be that number. Well, what's different about D?
It's cubed.
It's cubed. So what do you think we're probably going to end up doing to those numbers?
Oh, do we cube them?
So your answer to this is 8 over 27 for the same reason. Like I could show you all of the work to get D the way we just did the other one, but do you really want to do that? No. So some of these things you're going to start noticing patterns and your brain's going to tell you like this is what the answer is. And it's because we did the work in other problems. I don't want you to have to do it every time. It's the same thing as like A, the reason we can get A, we talked about A in our notes, is because you're going to end up multiplying by 5 over 5 so that this works out to 1. Well, I don't really think you need to do that every time. You just need to recognize that's the way it works, and the answer is going to be that 5. That's just why it works. So there are going to be shortcuts to these as we go through, and that's kind of one of them. Similar. Well, K is not really similar to that. K, you would see a little bit better if you kind of separated it. Sine squared is just really sine times sine. X squared is just x times x. So I'm just going to separate those. Now, we just talked about A. Without having to multiply by the 3/3 here, I know that this is going to work out to a limit of 3. This is going to work out to a limit of 3. Therefore, my answer to this question should just be what?
9.
9.
Is this kind of helping where we were with this?
Mhm.
Yeah. What did I not get to in question 1?
E.
E?
Yeah.
Okay, the tangent ones. Before I do E, let me
Did
look
you do F?
F first. Yeah, because F is smaller, maybe. You really can use kind of what you did in C to figure out F and E. Again, it's going to be kind of a process of using some of the shortcuts, but let me go back to F for a minute and then we'll go to E after that. Because my special trig limits have to do with sines and cosines, I would probably work with F and make tangent sine squared over cosine squared. I don't like double fractions, so I'm going to essentially think about making this x squared over 1 and flipping and multiplying, which is really just putting the x squared on the bottom. From here, it's just a matter of separating. I don't have anything to do with a cosine by itself. I have a 1 minus cosine, but I'm just going to kind of shove the cosine squared to the side and not worry about it. I'm going to keep that 2 out front. And just kind of like I did in K, when I have a sine squared and an x squared on the bottom, I'm going to think about that. And again, you don't have to write all of this out as sine over x, sine over x. And I'm going to leave this 1 minus cosine squared. Now, notice I really didn't do any work there. I'm just kind of moving things around to be able to think about it better. What did we say that limit is?
1.
1.
1.
That's going to be 2 times 1 times another 1. Is there any problem with plugging in 0 into the cosine?
No.
No,
it gives you 1.
that's just 1. Squared is 1. That's another 1. So my final answer for part F is
It's 2.
2 with a little bit of manipulation. So I would handle E very similar to that. There are probably rules you can use with tangents. Sometimes I don't worry so much about the rules if I know I can manipulate it, and tangents are pretty easy to manipulate. So I would start off with my tangent being sine of 2x over cosine of 2x cubed, top and bottom. Again, I don't like double fractions, so I'm going to flip and multiply, which means I'm going to have x cubed times cosine cubed 2x over sine cubed 2x. Again, I'm kind of seeing these as being good to be together, where I'm going to leave the cosine by itself. So I'm going to go ahead and think about that as x over sine 2x 3 times. Now, real quick review. We said our rule is sine over x. Well, what did we say in that other problem we did if it's x over sine? It's just the reciprocal, right? So what is going to be the limit of this considering the 2x and the shortcuts we talked about with that?
1/2.
1/2.
That's going to be 1/2, right? So it's going to be 1/2 3 times. So I'm going to just go ahead and cube it. Now go back to this cosine of 2x. If I plug in 0 there, what's the cosine of 0?
1.
1 cubed is just 1. So my answer to that question for part E is going to be 1/8. We'll cube all parts. Okay. 2a kind of follows what we were talking about. The reciprocal of sine of x. We said sine x over x is 1. If we flip that, we can just use the reciprocal of it. Technically, that's a 1/2. Okay, but we want to do the limit of that. If it was, let's just flip it for a minute. Sine of 1/2 x over x, what would be that limit? Using our shortcuts.
1/2.
1/2. So if we have the flipped version of that, what would be the answer to this? The reciprocal is just 2 for that. I mean, there's ways to do that, but I wouldn't really want to, honestly. So you could do it that way. You could use a calculator for that if you wanted to on that one. 3 D, I, and L is what I have here. Okay. Want me to keep moving? Yes.
Yeah.
Okay. D on question 3. My manipulation for this one would be changing tangent to sine x over cosine x, and then flipping and multiplying. That is keeping the top as sine x over 1, multiplying the or flipping and multiplying the bottom. What's going to happen to my sines? Right? So then cosine at 0 is just 1.
Did you do B? 3B?
Yes. I would have worked with the top first. Tangent is sine over cosine. I would have gotten a common denominator. Sine x cosine x over cosine x. So that's just for the top. I would have then made this sine x minus sine x cosine x over cosine x for the top and multiplied the bottom. So it's going to be 1 over x times cosine x. Let's see. There might be an easier way. I'm just kind of shooting from the hip on this one. That's going to be sine x 1 minus cosine x over x times cosine squared x. And here is where I started, I think.
That's where I stopped.
I feel like I did this one already and I remember what I did, or I think I remember what I did, but
I just got 0 for that one because you could just cross out the 1 over cosine x over x, and that's 0.
yeah, I think that is going to be what it ends up being, because if you take 1 minus cosine x over x, that's 0. Sine on top is fine because sine of 0 is 0. Cosine of 0 is 1. So there's no actual problem from there with plugging it in.
So you just kind of separate it into sine x over cosine squared x
Yep.
times 1 minus cosine x over x.
Because then you don't have a problem plugging it in once you have that special trig limit.
It just comes down to 0.
How did you get cosine squared x on the bottom?
On the bottom, that's from this cosine times this cosine.
Okay, thank you.
Okay. I'm going to keep moving, not because I'm not wanting questions. I just want to get through what we can because we do have to talk about a couple other things today too. I would use a double angle identity on that one for cosine of 2x. It actually works out quite easily. I would, because of the x squared on bottom, I tend to go with a sine for a lot of those. You could play with it and figure it out, but the double angle identity
Which
that was the sine one. 2 sine squared minus 1, is that right? No, that's the cosine. 1 minus 2 sine squared. Because then when I distribute the negative, the 1 minus 1 cancels, and that makes it positive 2 sine squared over x squared. And then from there, I'm really just thinking about it as sine x over x and sine x over x again. Because of
Which
this.
question is this?
Huh?
Which question are we looking at?
Oh, sorry, I.
Okay.
So that ends up just being 2 because each of these limits are just 1. Okay. L was the other one we talked about looking at on this one. If you can do I that way, if you didn't get this one, that one will work out very similar to that using those same rules. And there's a couple down in the bottom half, number 5, that involve the cosine of 2x, that if you use the right double angle identity, you'll be fine on those. L, tangents, I would always switch to sines over cosines. So let's make that sine over cosine, flip and multiply. That is going to be 3 sine of 2x over cosine of 2x. Oh, this one's going to be fun. Wait, that's a cosine of 3x here. I think I did this one already too. That's 3 over 1. Flip and multiply. That's going to be 1 cosine 2x over 3 sine 2x. What did I do on this one? I think I multiplied then by, there's already a 3 for under that sine. I think I multiplied by 2x top and bottom. Let's see if that does it. So then I can organize. Let me group things together. Sine of 3x over this 3 and this x. This sine of 2x under that 2x. Which leaves me cosine of 2x over cosine of 3x, which doesn't matter. This works out to 1, that works out to 1. Cosine of 0 over cosine of 0 is just 1.
What happened to the 2 on the far left bottom?
That's still there, so that's a 1/2. So that means my answer is 1/2. I lost that in my shuffle.
How did you simplify the cosine 2x or the cosine 3x?
Plugging in 0, it ends up being cosine of 0 over cosine of 0. The 2x's and the 3x's don't even matter.
How did you know to multiply by 2x? Like,
I was looking at the signs and I realized that if I could make that sine of 3x over 3x, I just needed an extra x. And then I looked at this sign and said that extra x would work for that, but I still needed a 2. This seems like probably more than I would expect you to do on that kind of question, honestly. They will tend to be a little bit more straightforward, some of these questions. So, other stuff, because we're 30 minutes in and still doing homework questions. I did address a couple of them in 5 in the video. A lot of 5, like A should be pretty straightforward. B should be not that bad. If you're having issues with other ones, the cosine of 2x ones should hopefully be a little more straightforward after we talked about I in question 3. Some of them, if they seem kind of harder, yeah, they are a little bit, because there's also people in this class that are working towards BC calculus that will need to do a little bit more, and there's some people that are not even taking calculus next year. So here's where there's kind of a mix of homework stuff that I'm trying to help some people prepare a little bit more than others. So don't
You said
for some of the harder ones.
for 5E,
Mhm.
we would treat that one like
You
one of the identities,
use the sum
right?
difference identity, but there is one that we didn't use on our formula sheet. If you look down toward the bottom, there's called the half angle identities, I think. And there's one that looks specifically like that. Sine of pi over minus x is equal to negative sine x. So you can use identities that we haven't talked about to shortcut stuff if you want to. They're still on your sheet, so you can still use them. Okay, are we somewhat okay to move on? Yeah, okay. For today, did we see that I posted a note sheet for today? Or no?
Yes.
Yes. Okay.
Okay.
It was on Canvas. If you want to pull it up quick, I mean, there's really, like, you can write down on a blank sheet of paper too. So let me pull mine up quick. This was a change because of having extra days and being able to spread stuff out. So it was under the lesson 9.4 stuff that we had. And I will share this so that you can see it. So today actually should be kind of straightforward compared to the last stuff. Trig limits tends to be the hard stuff, if that makes you feel any better. So asymptotes are what we were going to talk about today. We've talked about them a little bit already, but just kind of in general, speaking about both vertical and horizontal asymptotes and how to handle them. So quick review. Anyone remember how to find vertical asymptotes when we did this back in the fall?
You set like what's on the bottom equal to 0.
We set
Is that correct?
denominator equal to 0. How did we find holes in the graph?
You set something on the top equal to 0. Like when you cross something out.
Yes, that's when it is. So when we found factors that cancel. And we also set those equal to 0. So that would be like an x minus 2 over an x minus 2, and we could cancel that. Then we had a hole at x equals 2. Okay? Any problems with that? All right. So vertical asymptotes are a lot of the place where we're going to be finding that stuff just doesn't work right. Because if you remember vertical asymptotes, that was where stuff went like it splits. It goes up to infinity, down to negative infinity. But we also need to be able to like figure out where they are so that if you don't have a calculator, then you're not relying on the fact that you can't see the graph. So being able to remember that to find a vertical asymptote, you set the bottom equal to 0, and that you know when something is a hole, so you're not running into problems with that. So for our vertical asymptotes of that, let me find my official definition of that because I did not write it down here. I'm a genius. Did I put that? Excellent. Well, we don't really need the definition of it anyway. In other words, a lot of times at vertical asymptotes, we're going to end up being or having a does not exist. You can do one-sided limits. If it's tracing it in from the left or tracing it in from the right, you can say that it's going to positive or negative infinity. But a lot of times the official limit is going to be does not exist. For horizontal asymptotes, do we remember what those looked like or how to find those? This was also rational functions. We had a lovely mnemonic device that we used for these. Anyone remember what that was?
Oh, is this like the B-O-B-O? Yeah, Bobo, Botan.
Eats DC.
That's it.
Okay, if you remember that, that's what's going to help you find horizontal asymptotes if you don't have a calculator. And really relying on our calculator for some of these is not the best idea because the graph is not going to be specific enough to show you the exact numbers that these are at. So remember what this stands for. The first one, Bobo, is bigger on bottom. That's your exponents are bigger on bottom. Then you have y equals 0 as an asymptote. The second one was if the exponents are bigger on top, there is none. And then the third one was if the exponents are the same, you divide your coefficients to find your vertical or your horizontal asymptote. Okay, so those are going to be y equals ones, where your vertical asymptotes are going to be x equals. Often, though, with the horizontal ones, this is going to describe the end behavior of your graph. So that's what we're going to use the horizontal asymptotes for. So starting with an easy example on example 1 right here. I don't have to factor, I don't have to do anything with this, but we can figure out what's going on with this without using a calculator. That's kind of the point of what we're talking about today. Just kind of having parent function knowledge. and just a general idea of what the graph would look like. So if you remember back to rational functions, we graphed these without using our calculator. To find the vertical asymptotes, as you just said, we set the bottom equal to 0. So I'm going to have a vertical asymptote at x equals what?
1.
1. Horizontal asymptotes, we go through Bobo, Button, Eats, DC. If there's no x on the top, technically my exponents on the bottom are bigger. So bigger on bottom means we have a horizontal asymptote where?
0.
0.
Y equals 0. Okay, now at the beginning of this, in order to evaluate these limits, we have 4 limits to find. The limit as we approach 1 from the left and 1 from the right, and then the limit as we approach infinity and negative infinity. And these we have not seen at all yet. And this is all based off of vertical and horizontal asymptote behavior. Some of you are more visual than others, and I am not saying to draw a very specific graph here at all. Like this should take 30 seconds or less. But if you had to draw a little sketch of what this looked like, we have a vertical asymptote at 1. We have a horizontal asymptote at 0. Okay. This means our graph is going to be split into 2 pieces. Any ideas as to where one of them is going to be?
Top
Will it be
right.
in like the top right and then like the bottom left?
No, if it's the top right, bottom left, or diagonal the other way.
I just plugged in numbers.
Okay, so the easiest number to plug in is 0 right here. That's going to tell me where the y-intercept is. If you plug in 0, it's going to be 1 over -1, which means my y-intercept is here at -1. And that takes like half a second, right? So you're going to just do this real quick and see what it looks like. And then using that information, we can then find these limits. So looking
Wait,
at
isn't the asymptote at -1 for the vertical asymptote?
no, it's that positive one. Because if you set the denominator equal to 0, you're going to add 1 to the other side.
Oh, okay.
Okay, so then notice over here around the vertical asymptote that we are asking only from the limit as we approach from the right and from the left. They have not actually said the limit at 1. We're going to talk about that. But a lot of times with vertical asymptotes, that's what you're going to see because they want to know where are these heading off to. So if you had to tell me what is the limit as we approach 1 from the right, what would it be?
Of infinity, right?
Infinity, right? And then as we approach 1 from the left,
Negative infinity.
Negative infinity.
which would mean if I did ask the question, what is the limit as x approaches 1, what would we say?
Doesn't exist.
Doesn't
Doesn't exist. Now, notice that when we do the one-sided limits, the left and the right, we do put infinity or negative infinity. That doesn't change the fact that the limit doesn't exist. Really what you have to remember is with these infinities, that's another way of saying it doesn't exist because you really can't get to infinity. You can't say the limit equals a number. It doesn't work that way. But you're being more specific. You're saying it doesn't exist because that branch is headed off to infinity. It doesn't exist because that branch is headed off to negative infinity. So it's still a more specific way of saying does not exist. But now, the other two, these new ones, we have not talked about. The limit as x approaches infinity. We always freak out about these because we're like, well, where's infinity? How do I find that? This is just end behavior. If I am asking you as the graph is going off to infinity, which part of the graph are you going to follow?
The right side.
The part headed off to the right. So I'm going to trace this graph as it heads off to infinity. This is just end behavior. We did this with exponential functions, with rational functions. As that branch heads off to the right, what's it getting closer and closer and closer to?
0.
Yep. Notice that those are going to always be the horizontal asymptotes. So your horizontal asymptote is going to give you information about the limits at infinity and negative infinity. So it's going to work the same way as we follow out to negative infinity. This time we're going to follow the part of the graph that's headed which way?
So
To the left, right? So the branch that's going off to the left is this guy. And as it goes off to the left, even though it's on the negative side, it's still getting closer and closer and closer to that horizontal asymptote, which is at what?
0.
0. So without using a calculator, using our knowledge of vertical and horizontal asymptotes, we can find a lot of this information on our own. Okay.
Why
Question
isn't it infinite or like infinity or negative infinity?
for these?
Yeah.
That would be if this part was going something like that. That would be going down to negative infinity, because you're asked for the limit as x approaches infinity and as x approaches negative infinity. So like for the left side, for example, as x goes to negative infinity, you are following the part of the graph that continues to go left. This part of the graph is getting closer and closer to x equals 1. It's not going out to negative infinity. This part of the graph is what's headed out toward, and the x keeps increasing towards negative infinity. So that part of the graph is what's getting closer and closer to the horizontal asymptote. You could have a graph that does something like that, and then it would be going towards negative infinity. So that is possible, but not in this particular one. Any other questions on that particular one? All right, I have three more examples we're gonna run through real quick, maybe. And honestly, it may just be, I may leave off or go quickly. We'll see. All right, so example 2. Remember with these rational functions that before we did anything else, what did we always do?
Factored.
Did we factor them out?
Always factor, yep. So this factors into x minus 2, x plus 1. The bottom factors into 2x, and x factors of negative 6. If I want it to add up to negative 1 in the middle, I got to do negative 3 here and positive 3 there, negative 2 here. Yes. Okay. And before we did anything else, what did we say about the factors top and bottom if there was one that was the same?
Isn't that a
Cancel it
whole?
out?
Yep, we can cancel it out. And that's going to be a hole in the graph at x equals 2. They're not asking about that right here, but what's important is that that x equals 2 is not a vertical asymptote. So now when we're asked to do part A to find the vertical asymptotes, I now set what is left on the bottom equal to 0. So I have a vertical asymptote where?
Negative 3/2.
Negative 3/2. I have a horizontal asymptote. I'll fill in D here. Horizontal asymptote, Bobo Button eats DC. Which category are we in?
Each DC.
And I go back to the original for this one and just divide these numbers right here. So that tells me my horizontal asymptote is at y equals 1/2.
Wait, why is it that again?
Because the exponents are the same, top and bottom.
Ah, okay.
And it does ask for holes in the graph. So we have a hole in the graph at x equals 2. What does that mean about these limits? Do I have to use a graph to find the limit as we approach 2 from the left and 2 from the right?
No.
No, because if it's a hole, what does that mean I can do now with this simplified version of the function?
Just
Is it a
oh,
plug into?
yes.
Yes, it is. So I kind of categorize them even based off of what it is. Like a hole, you're going to be fine plugging in a number after you cancel something out. If you have a vertical or horizontal asymptote, I consider the graph for those. So if I'm approaching 2 from the right and 2 from the left, that doesn't necessarily mean I have to use a graph for that. I can just use my simplified function, and it's going to be the same answer for both if you can get a number out of this. So it gives me 3/7 for this. So if you have a hole, you can always plug it into the simplified version after it cancels out. Always works that way. If we want then the limit as x approaches -3/2, which is our vertical asymptote, I would consider the graph for that one. So quick kind of sketch of what that would look like. I have a horizontal asymptote at 1/2. I have a vertical asymptote at -1.5. And then the easiest way to see where one branch is to plug in 0 to the simplified version. 0 would give me 1/3. 1/3 is in fact less than a half, right? So that means I'm going to have a branch here with a hole at 2, which if you want to draw it in, go for it. But there we have it. Which means the other branch would be up here. So what does that tell me about the limit as x approaches -3/2? It doesn't ask from the right and from the left. What is it telling me?
It
It's not
doesn't exist,
Doesn't
right?
exist, right? Because the two branches, one goes off to infinity, one goes off to -infinity. So often, well, always, at a vertical asymptote, your limit is not going to exist. Now, can I find the limit as x approaches infinity and -infinity? Okay, so let's go back to looking at the graph there. As x heads off to infinity, which side of the graph are we following, the left or the right? As x heads off to infinity, we're following which part of the graph?
The right side.
Right side. So I track the part of the graph that's headed off to the right. That's going to be getting closer and closer and closer to that asymptote, which is where?
1/2.
And same thing, as it heads off to -infinity, we track the left side of the graph. So that's tracking this branch, heading off to -infinity. Okay, that's going to also be approaching the horizontal asymptote of 1/2.
Miss Leininger, to know where like where to put it in the second and fourth quadrant, is it you just plug in 0 again?
Plug in 0, yeah. It usually gives you enough information unless the asymptote's at 0. Then I pick another one to plug in.
Did you plug 0 into the original or to the simplified?
I plugged it into the simplified only because it's less numbers to plug it in. I'm really short and sweet with that one. Or remember that the other rule for plugging in 0 is that it just ends up being those numbers right there. So -2 over -6 reduces to that 1/3 that we used as well.
Where did he get the horizontal asymptote again?
Bobo button eats DC. These are exponents are the same. So we divided our coefficients in front of those highest exponents, and that gives me that 1/2. Other questions on that one? Let me look at 4 real quick because 3 is different and we may or may not need it. So just hang on with that. Example 4 real quick. Anything I can factor?
Yeah.
The
Like-
X on the bottom.
X top and bottom, or really top. So there we can cancel one of our X's. What does that tell me?
You have a hole.
Where?
1.
If
1
it's
over X.
X, what is it? It's 0. Because you're just setting X equal to 0, right? So because I canceled 1X, that means I have a hole at 0. Where do I have a vertical asymptote?
At 2.
At 2. And horizontal asymptote, think original, simplified, doesn't matter. Bobo button eats DC. What's true about my exponents here?
Bigger on the top.
You're on the top. So that means what about my horizontal asymptote?
There isn't one.
Isn't one. So we're going to see what happens with that in just a second. And that's the reason that we're really looking at this question, because notice it doesn't ask for any other limits except the limits at infinity, which the limits at infinity always are affected by this horizontal asymptote. So let's kind of see what's going on with this graph. If I just drew a little sketch of what it would look like, I know I have a hole in the graph at 0. If I go back, I have a vertical asymptote at 2. If you plug 0 in to the simplified version, can you still get a number back out for that hole?
It's 0.
It's 0, right? So you have a hole at 0, 0. Doesn't necessarily tell me much about what this looks like. You could continue to plug in numbers and see what's happening. But really, if something has like weird behavior, what do we tend to do?
Graph it.
Graph it.
Um,
Yeah. So real quick, let me pull up my calculator for you. Glad I had that pulled up in advance. Whoops, where is it? Cancel. Go back. Let's see what our graph would look like. And you can graph the original version or you can graph the simplified version. Doesn't really matter. I'm going to just go ahead and delete what I have in here so that I can start fresh. All right, so we had the simplified version. I will always use the simplified version because it really just doesn't matter. X minus 2. So this is the kind of graph we had. Remember real quickly out of what we talked about in rational functions, that when it did not have a horizontal asymptote, anyone remember what it did have? Anyone remember slant asymptotes?
oh.
I'm not going to make you find the equations of them. But what does it mean then for this? And I'm going to zoom out a little bit so that we can see the rest of it as well. Because remember that these were the ones that always have 2 branches, but they're these little curvy looking ones. Here's my graph. So if I am then finding the limit as x is approaching infinity, I'm tracking the part of the graph that's headed off to the right. All right, so that is this part. Where is that going to go?
Infinity.
Infinity. Now track the graph that's headed off to the left side.
Negative
It
infinity.
goes there, it goes to negative infinity. So what you're going to see on a lot of the ones that don't have a horizontal asymptote is those kind of limits. So limit as x goes to infinity is going to be something like infinity or negative infinity. And they don't have to match on that. So just check a graph for that is kind of the moral of that story.
So how do we know when we have to graph it or not?
If you don't have, like this one, when I tried to graph it on my own, I got to the vertical asymptote and then a hole at 0, 0. Is that enough to know what's happening?
No.
No, that's when, honestly. I'm not at this point making you go back and be able to find slant asymptotes because they're a little bit, but use a graph when, limits is hard because it's not one of those, I would have to give you a calculator for almost every question because that's always an option. Like it's always an option to not have enough information and then have to go check the graph. That's just how limits work. A lot of these you will be able to, like we did in example 2 or example 1, draw a brief sketch yourself and see what's going on. But it's like what we did in rational functions. If there's not enough information from what you find, the vertical, horizontal, holes, all that, and you can't just plug in a number to figure out something like we did before, then use your calculator. So we're getting to the point in some of the stuff that we're covering that like I really focused on not using a calculator to make sure you get through knowing how to do stuff without one. But you start to get to the point that like, we're going to use it as a tool when we need it. And that's kind of how calculus works, honestly. It's there if you need it and you should be able to do stuff without it. But, you know, that's kind of how that works. Your homework for this is also uploaded here. Let me share that on Canvas as well before I sign off because I had another thing at 10 here. This lasted a little bit longer, but hopefully that helped with homework. Your homework is listed here for you. Just know for this kind of thing that your calculator is an option if you need it. So your homework for this, a lot of it's just kind of end behavior stuff. So real quick, just looking at the beginning of this, giving you a place to start. Let's think back to polynomials. This is a 3x to the 4th. Anyone remember what the end behavior of an x to the 4th is going to look like? No one? Remember this, whether it's odd or even degree?
It's gonna be in the same direction, right?
Positive or negative leading coefficient. Even means both ends go up if it's positive, both ends go down if it's negative. Odd is down, up. Negative is up, down. So, for example, like so many of these beginning ones, you're just using this chart. Because it's a positive leading coefficient and a fourth degree, I know both ends go up. So as x goes to infinity, where's the right side going to be going? Hello? No one knows? It's even positive. That means both ends go where?
Up.
Up. Therefore, the limit is infinity.
Oh.
When it's even, when you say even, do you mean for the exponent or the?
Even highest exponent. So a lot of these are going to be based off of this. So very similar, same kind of question. Well, it is the exact same question, except it's going to negative infinity. Does that matter if both ends are going up? Does that change my answer? Where does that go?
Still to infinity.
Still infinity. C is a negative, but an odd degree. So that's this right here. So as x goes to infinity, where's the right side going to be going?
Negative infinity.
Negative infinity, and then use the same thing. So honestly, I'm going to use that for most of these. Because you should be able to still stick with that, even if it's a different kind of looking one. You may have to think about parent functions for some of these. If you can factor then in question 4, that's where we're going to go with that. So when, let's just go back to this. Remember that limits at infinity have to do with horizontal asymptotes always. So when I get down to something like question 4, I am really concerned only with where's the horizontal asymptote, okay? So if I'm looking at 4, I'm thinking Bobo button eats DC. Highest exponent on top is 2, highest exponent on bottom is 3. What does that mean the horizontal asymptote is?
None.
Figure on bottom is
0.
0, which means the limit as we get out to infinity on either side is going to be 0, because it always goes out to that horizontal asymptote. So a lot of 1 through 3, you're going to use that chart to think end behavior, just where is it going? To be very honest, there should be very few of those that you check a graph on your calculator. Even down in this bottom section, these are exponential functions. We talked about that and where to find the asymptotes for those. So as long as you can identify where the asymptote is for these kind of questions, you should be able to identify what the limit's going towards without checking your graph. You may want to use your calculator to double check, but that's just kind of it on that. Okay.
What about a question like 2E?
2E. Highest exponent is the third degree,
Okay.
and that's the negative leading coefficient, so you should still know which way the ends are going.
Okay.
What about x to the 4th under the 12? Is that not?
A negative one because it's on the bottom, so it's not the highest exponent. It's actually the lowest.
Okay.
Okay. All right. Quiz today only over the first 2 lessons, so not the trig limits. It's really just like the graphing and the conjugates, factoring, complex fraction stuff, which we all seemed okay on. The trig stuff will be incorporated into the test, but not before then. And this is our last quiz. Yes, you do have to try it to be able to drop it. If it's your worst one, the limits test would be horrible if I let everyone not take this quiz. But we're finishing up. It's going to happen really quick. All right.
Do we need to explain anything on the quiz?
Yeah, so the way it's set up is the beginning of it's graphing stuff, kind of like where you just found the limits off of a graph. You don't have to explain those. The directions tell you. So it's 10 questions again. The first question's all off of a graph. Don't have to explain that. And then 2 through 10. Explain what you're doing. The programs still do a little too much for me to not feel like we need to explain. So continue doing that. All right.
Where is that extra video you were talking about earlier?
It is under my announcements in Canvas. Let me see if I can share that real quick. Because it's about a 10-minute video that answers some more questions on that other one. That was, let me see if I can find it. Announcements. There should have been one on Friday. Questions on 9.2 and 9.3 homework on your announcements. And there's a video linked here for you.
Okay.
Alrighty, folks. Anything else I can help you with? All right. We're going to sign off then.
Thank you.
Yep. Y'all have a good afternoon.
Thank you.
Thank you.
Bye.